Hey everyone, my name is John Jackson. I am a PhD student at the University of Colorado Boulder. I've been working with Dr. Laurenti at the University of Oxford and Professors Frew and Lahijanian, also at CU Boulder. And today I'm excited to talk to you about safety verification of unknown dynamical systems via Gaussian process regression. As autonomous systems become more complex, certifying their behavior in safety critical scenarios becomes more important and more challenging. And this challenge is just compounded if there's any source of uncertainty in this scenario. Consider this small unmanned aircraft system flying in an urban environment. We might have an incomplete dynamics model of the aircraft, so we don't know where it's going to end up in the future. There might also be wind that affect the dynamics of the aircraft that we just can't know beforehand. And there's also other vehicles flying around in the environment. So in this scenario, it's very important to respect any safety constraints, whether that's staying below a certain flight ceiling, staying out of any restricted zones, and in general, just staying safe and not crashing. And failing to take this into account will lead to property damage, no doubt, and in the extreme case, loss of human life. So while we're designing these vehicles with safety in mind, we can leverage the power of formal methods to try to certify safe behavior of the unknown system. So traditional model-based verification uses an abstraction of a high fidelity model and a safe set to do safe set reachability. In this scenario, we want to ask, will this system stay within the safe set over some period in the future? So the answer to this question is either yes or no. However, if we use a simpler model, such as a linearization or just anything else, the guarantees that we generate for this simple model do not necessarily apply to this high fidelity model. So this begs the question, how can we work with these simpler models but still get guarantees for higher fidelity models? And one way to do this is by using a data-driven verification approach. So this involves collecting noisy data on our unknown system, learning some estimate of the dynamics, and then generating verifications in one way or another. So the goal is to do this in such a way that these guarantees that are generated apply to the underlying system, here called the quote-unquote true model. And other people have looked at this before. Prior work has considered only linear models, and others have tried to learn nonlinear models but don't tie it back to the underlying model. So this begs the question, how can we generate these guarantees for potentially nonlinear systems and still tie them back to the underlying model? So our framework does this by extending existing model-based verification techniques. And I will first give an overview of what the problem looks like. So we have a discrete time system here where this dynamics mapping F to the next discrete state is unknown. We have noisy observations of the state where this noise is IID and bounded. The state space is continuous, and we have a discrete set of control inputs, which might be different control laws or control primitives that we have. So here we're given a data set generated by the system. We're not considering any sort of online approach. So given this data set, we want to ask the question, if the system is initialized at x naught, what is the probability that over some fixed time horizon, it will stay within this safe set given by this black rectangle? So we want to ask this for any initial state within the safe set and identify those that have a high probability and a low probability of remaining safe. And this verification problem does this for any arbitrary control policy. So with this problem in mind, I will give an overview of how we solve this problem. So given this unknown system and the data set that it has generated, we use Gaussian process regression to estimate the unknown dynamics function. By making continuity assumptions on the unknown function, we can generate high probability error bounds on our regression. We use these errors to come up with an interval markup decision process. This IMDP abstracts the unknown system in a finite state representation. And finally, we perform reachability on this IMDP to find probability bounds on remaining within the safe set if we start at each one of these states in the IMDP. So I'll briefly summarize the important parts of each one of these components. Gaussian process regression is a very popular non-parametric machine learning approach used for regression. So given some prior mean and covariance function and a noisy data set generated by the system, the procedure is to make the standard joint Gaussian assumption on these priors in the data set, and then just use Bayesian conditioning to come up with posteriors. And from that, we get this maximum likelihood estimate of our dynamics function and a posterior covariance that we can use to come up with high probability error bounds. Now, if we assume that the unknown function f lies within the span of the prior covariance function, which is called the reproducing kernel Hilbert space, we can use existing results for bounding the error between the unknown function and the regression that we get. And this is in terms of some delta value that scales with the interval that we're considering. And from this, we can get high probability error bounds. And the reference for what we've used is available at the end of the PowerPoint. So next, and most importantly, we construct an interval markup decision process using these error bounds. The first step is to come up with a finite number of states. And we do this by doing an appropriate discretization over the safe set. And we also add one more state to the IMDP that just captures everything that's unsafe. So the next step is to consider how do we transition from one discrete state to another. And in general, we can't calculate the probability of transitioning from Q to Q prime because of the nonlinearities involved in all the uncertainties. So instead, we do a bounding of the transition probabilities to get a lower bound and an upper bound. And to do this, first we need to come up with an approximation of the image of Q, or propagating Q through the unknown dynamics. Once we have this image of Q, we can look at first an expanded version of Q prime to come up with an upper bound on the probability of transitioning from Q to Q prime. And then we look at a shrunken version of Q prime to come up with a lower bound of transitioning from Q to Q prime. Details on how these transitions are done can be found within the paper, but the important part is that these account for discretization and regression error. And using these transition probabilities, we can construct our interval markup decision process, where for any given action, the transition probability from one state to another is given by an interval. So finally, we can do verification over this IMDP, which consider state Q2 here. We want to find the probability of remaining safe, which is the 1 minus the probability of reaching this unsafe state over some fixed horizon. To do that, we do value iteration over all possible choices of control and all possible choices of the transition probability distributions to get a lower bound and an upper bound of remaining within the safe set. And given this interval, we can then classify each state by looking at the lower bound in some p-value, here 95%. If the lower bound is greater than 95%, we mark it as safe according to this p-value. If the upper bound is lower, we consider it unsafe. And then every other state that falls somewhere in between are those where we can't generate guarantees. So that's our approach in a nutshell. In the paper, we show that by capturing the paths of this unknown system in the IMDP, the guarantees that we generate do apply, in fact, to the unknown system, closing the loop. So by using this IMDP to capture an abstractor system, we can finally generate guarantees for the unknown system. So now I'll talk about a couple of examples that are presented in the paper. The first is just a 2 control mode switch system represented by these upper diagonal and lower diagonal matrices. I trained GPs with 1,000 data points and relatively low noise, and we get on the right a minimum probability of safety. That is, for this safe set given by this 4x4 square, initial discrete states classified with a certain minimum probability of safety. And here they all are near 0 or they're near 1. So you can interpret this as if I initialize the system in any of these white cells, after 1,000 steps, the probability is close to 1 that it will remain within this overall safe set. And we can't make this guarantee everywhere. The minimum probability of safety is 0 in these corners, in a large part due to uncertainty that we haven't accounted for. And because you can see from the system definitions given here, in fact, some of these control modes drive the system outside of the safe set. So next is a single mode nonlinear system. And this has a sign term in the second component here, and the vector field is given by this circular looking vector field. And it did the same thing, collect data on the system, come up with GPs, and generate verification results for different time horizons in the future. So after one step, since the system doesn't change very fast, we can guarantee safety in a large part of the safe set. And as we consider 2 steps and 6 steps, this shrinks considerably, just because this is an inherently unstable linear system. However, we can still verify safety for some finite number of steps. So this is super exciting work. There's a lot more work to do, including, so a lot of the choices in this framework are parameterized. So I'm currently investigating optimal ways to choose them. And in addition, there are some cryptic RKHS constants that aren't super straightforward on how to use. So I'm working on a way to bound those in an easy way. And then I think most exciting is extending this to online verification and the synthesis problem. That is, given some learned model and a property such as this LTL formula given here, how do I synthesize an optimal control policy that will satisfy the specification with a high probability? So that is our framework. We have done verification of an unknown dynamical system by taking a data set that's given to us, learning about it, and using high probabilistic error bounds to come up with an abstraction and generating guarantees on that. So there's much more detail in the paper. I'd be happy to talk about this work in the future. And thank you so much for listening to my talk.